Hello everybody, welcome to the first offline recorded lesson for the reinforcement learning class. As mentioned in class on Monday, we're going to talk first about probabilistic reasoning and learning, and then probabilistic reasoning over time, and then we're going to move on to Markov decision processes and reinforcement learning. So the topic of interest for us for today is going to be Bayesian networks. And we're going to talk still a bit about probabilities. But before doing this, let me highlight for you the Slido code. Let me remember that you can use this code in order to ask questions that are related to this class and to vote questions that your colleagues asked and that you find relevant too. As well as to propose topics that you would like to talk about in class. Now let's start with our actual class, and we'll start by talking about the Wumpus World. So the Wumpus World is a grid word that you will find in any artificial intelligence book. So you will find this also in the AI course from Professor Nardi. But today we're going to talk about a simplified version of the Wumpus World. And in this simplified version, in our example, we are considering a 4x4 grid. And in each, so we have 16 cells, and in each cell we can have either pits or breezes. So breezes are actually caused by pits. So if in a neighboring cell we have a pit, then you can have a breeze in a certain cell. So this is the case, for example, in cell B12, where we have a breeze, and in cell B2 in cell 21. Sorry. So this means that in the neighborhood of these two cells there is some pit. We also know that in cell 11 we don't have any breeze, and that in cells 11, 12, and 21 we have no pit. In addition to this, we also know that each square except 1 contains a pit with probability 0.2. So this is our prior. Cool. Okay. Let's now move on. So what would you like to do with this? You would like to probably reason about where pits are located, given the fact that we know some information regarding the breezes in cells 1, 2, and 2, 1. In order to do this, we need to create our probabilistic model, and our probabilistic model will be composed of some random variables. So what are the random variables that we can consider? We can consider some Boolean random variables. So Boolean that can assume values either true or false. And in specifically we can define random variable for pits and for breezes. So we can define 16 pit random variables for each cell, and this will be true only if and only if the square ij contains a pit. Additionally, we can create random variable breezes with breeze ij, which is true if and only if the square ij is breezy. Actually, what we have to do in this case is to include these random variables only for the observed squares, because given the pits, we don't know exactly how the breezes are distributed. So we can only talk about what we see. So we know information about cells 1, 1, 1, 2, and 2, 1. And we include this in our probability model. So we have 3 Bij. Okay, so now we can first of all define what is the full distribution of this whole thing, which is basically the probability of all the pits and the observed breezes. And using the product rule, we know that this is the same as the probability of the breezes given the pits, multiplied by the probability of the pits. So this term here will be 1 if the pits are adjacent to the breezes, and 0 otherwise, while this term is nothing else than the prior that we talked about before. And given that all the pits are independent from one from the other, so there is no relation between a pit in this location and in this location, while there is a dependency between breezes and pits. As a consequence, we know that we have this prior probability of 0.2 per square, and we can compute this term for n pits as basically the product of all the probabilities. So this is going to be 0.2 elevated by n for the true value. So this is for true, and this is going to be our value for false. Now we know all this information, and we're going to use this in order to compute the answer, probabilistic answer, to this query here. So what is our query? So we want to know what is the probability of the fact that there is the probability of having a pit in cell 1, 3, given what we know, which are information regarding cells 1, 1, 1, 2, and 2, 1. So let me again color this for you. This is what we know. While the unknown includes all the other things, and here there is also what we call the fringe. Of course, in the unknown we don't have the item that we're querying for. So let me recap here. Also, what are the known facts? We know that we have breezes in cell 1, 2, in cell 2, 1, and we do not have a breeze in cell 1, 1. We also know that we don't have a pit in any of those cells. Okay, so now how do we compute the answer to this query? So definitely not by enumeration, because this becomes quickly hard to do, considering that we have all these terms. However, we can try to use some smarter relation between the information that we have and the information that we don't have. So here we can apply the product rule, and so we know that the probability of the having a pit in cell 1, 3, given the information that we have, so the known and B. So what is B again? This is B. So the breezes. So given this information, then this is equal to the joint probability of all these terms, which are the item for which we are querying, the known, the B, and the unknown, by summing over all the unknown. Right? Okay, so let's reason a bit now. I mentioned here, this becomes quickly untreatable because all these unknown terms are a lot, and so we have this number of computations to do, which is unfeasible for us. So we need to be smart. And how can we be smart? We need to do some considerations. Are all squares relevant for us? Can something in this cell affect in any way something here, or actually in cell 1, 3? No, right? Because we know that breezes are caused only by neighboring cells, so this is something far away. And moreover, we are reasoning about pits, and pits do not depend from anything else than maybe observations of breezes around in the cells around. So this is the reason for which we define what I have tried to highlight before, which is the fringe. So the fringe defines basically where we need to look at something that is actually relevant for us. Known is known, and other are everything else that is not relevant for us. Okay, let me switch cell now. So let's go back to our first formula, and please do not scared by looking all these formulas. We'll go through them together, and you will be understanding those very easily. So as I mentioned before, here we are using the product rule, and we said that in order to compute the answer to our query, we need given the known information and the breezes, then we can use the joint probability distribution between the query, the unknown, the known, and the b by summing over all the unknown and using this normalization factor. So in order to clarify, here we are doing this probability of a given b is the same as probability of a and b divided by probability of b, which becomes nothing else than alpha multiplied by probability of a and b. Why? Because this is a normalization factor. So now, sorry for having written in a place where maybe it's not very visible that this was anyway, just a recap for you. Okay, so this is our normalization term, and now let's focus on this term here. What do we have in this case? So we actually have that b depend on this other information. So breezes depend on pits and not vice versa. So we can compute this term as the probability of the breeze given the query, the unknown, and the known multiplied by the probability of the query, the unknown, and the known. So here we just used the notion of conditional dependence. So yeah, conditional dependence led us here to this step. What happens now? So we have divided already the unknown in frontier, so the fringe, and the other. So let's do the same here. So the summation over the unknown becomes nothing else than a summation over the frontier and the other. And so we're going to just write this in terms of frontier and other. Again, so we did nothing crazy. And by doing this, we can also notice that breezes will only depend on the query and the frontier, and not on the other, and the known of course, but not on the other. So we can get rid of this term here, because of they are independent from each other. So here we're going just to leave the probability of B given given our query, our frontier and unknown multiplied by the term that we also have up here. And this is going to result, again, here we're just moving the summation from the outside part, so summation to other, we're going to move it inside here. Why? Because this term doesn't contain any other information. And finally, we're going to do the same thing that we did here in this step. So we're going to look at this, and we're going to use conditional. We're going to use the fact that this is a joint probability, and these terms are all independent from each other. And so we can compute this just as a product of all the individual probabilities. So this summation of the joint probability will become just a summation over the probability of the product of the probability of the query, the probability of the known, probability of frontier, and the probability of other. Now here we're just moving out known outside of the summation, because known is not used in any in any summation. We are moving for the same reason outside probability of P13. So this becomes our new alpha prime. You will see that this will become our new alpha prime. But anyway, so we have now only these terms that are just a rewriting of what we had before. So as I mentioned, this term is actually going to become, together with this, our new A prime. Okay, so we're keeping our query, of course, here because this is relevant for us, and so our formula will become, again, probability of our query given the known and the breezes is the same as a normalization factor multiplied by the probability of having a pit in 1 tree multiplied by the sum over the frontier. And now, as you notice, we only have the frontier. Actually, let me clarify why we moved this term in alpha prime. Why? Because this is nothing else than the multiplication of all. This is nothing else than summations over all the priors. Right. So also these are easy to compute, so we can actually compute this because we know that the probability in each pit is 0.2 for having in each cell it's 0.2 for having a pit, and as a consequence we're going to use this information and embed it inside alpha prime. Back to these slides. So we're now here where we are left only with the frontier as we imagined. So now basically we're computing the probability of the breezes given the fact that there could be a pit in 1 tree, the frontier and the known multiplied by the probability of the frontier. So these are the probabilities of the frontier. In fact, by using all the possible combinations, we know that we can have first of all we can have a pit in our query cell, which is 1 tree, or not have that. and we're basically here computing all the possible alternatives that we can have. And then we're doing all the computations that we need to do by actually using these numbers. So here we computed with this case being with P12 being true. So this is the case where this is true, and this is the case where this is false, where P13 is true or false. So in the case where this is true, right, which are these three, and this is true, this is false. Okay, yes, so in this case, when this is true, we can have all these situations, so both 2-2 and 3-1 have a pit, or only 2-2 has a pit, or only 3-1 has a pit. Vice versa, we can have, if this is false, we can have a situation where both 2-2 and 3-1 have a pit, and only the situation where we have a pit in 2-2 and not in 3-1. Why this is the case? Because if we had a pit in 3-1 alone, we wouldn't have a breeze in cell 1-2, because we don't have anything here, we don't have anything here, so a breeze here is not justified. So now we use all these numbers, and we make all our computations, and we're done. So here we're again multiplying 0.2, which is the probability, this probability here, right? This probability here by these numbers, the sum over all these numbers here, and 0.8 here. Why is 0.8? 0.8 is just because this is 1 minus 0.2, which is the probability of having a pit in a certain cell. What else do we need to discuss from this slide? So actually we took into account, if you think about the reasoning that I did here, so I talked about the fact that here we cannot have the case where only 3-1 has a pit, and this is already taken into account. This dependency of the breezes on the pits. So this is why in this computation we are not using any term related to that, because we already took into account this part here. Okay. So this is one way of reasoning about things. And as you noticed, what we did is that we used a lot the information regarding independence between things. And we noticed that this is actually key for us to get rid of very complex computation and many enumerations. So we went from something like this number to listing only 5 cases and making a summation and product by hand. Again, we used the information regarding independence, and actually something that helps us a lot is the Bayes rule. Actually, the Bayes rule defines for us a clear notion of independence, and this notion of independence is used in Bayesian networks. So what are Bayesian networks? A Bayesian network is actually something like this. This is a Bayesian network for us. So it's a graphical notation that clarifies conditional independence assertion, makes them very clear in a very visible and compact representation, and this represents actually a full joint distribution. So this is the semantics of a Bayesian network. So the full joint distribution can be represented of some random variables, so the full joint distribution. Okay, let me repeat this. The Bayesian networks represent a full joint distribution of random variables. So this is the global semantics of a Bayesian network. Now, as in terms of syntax, this is very easy. We have a set of nodes. Here our nodes are weather, cavity, toothache, and catch, and this is I directed acyclic graph. So we have edges between these nodes, and basically a conditional distribution for each node is given by its parents, meaning that we have probability of a certain node depending on the parents on that node. So in this case, for example, in the example that we have been looking at, weather, right, doesn't have any parent. Here, weather doesn't have any parent, so it's independent of any other variable. Instead, toothache and catch are conditionally independent from weather. They depend on cavity, but they become conditionally independent from anything else once they are given cavity, when the information about cavity is given. So let's look at one example. So let's say that I am at work and I have two neighbors, John and Mary. So a neighbor, John, calls to say that my alarm is ringing, but neighbor Mary does not call. So sometimes this alarm is set off by some minor earthquakes, and the question is there a burglar? So how can we set up the problem? Let's define again our probabilistic model, and in order to define our probabilistic model, we need to identify what are our random variables. So in this case, our random variables are the following. We have a burglar, earthquake, alarm, John calls, and Mary calls. And then in our network topology, we will try to reflect causal knowledge as it is listed in this small text, which is specific that a burglar can set the alarm, an earthquake can set the alarm too, and the alarm can cause Mary to call, and the alarm can cause John to call. So let's try to write it down in terms of a Bayesian network. So we have created our nodes, which are burglary, earthquake, alarm, John calls, and Mary calls, and we have created our edges. So these edges will go from parents to children. So we know that a burglary and an earthquake can cause the alarm to ring, and that the alarm can cause John to call and Mary to call. Now here we're defining here in these tables something that is called conditional probability. table. CPT. So as you can see in our conditional probability table, basically we are listing all the possible values for all the parents and associating a probability for the alarm depending on these values. So to be very clear, here this is the probability of the alarm to be true with these conditions. You can imagine like whether there was an additional extension to this table here where this is false, and so this would be 1 minus 0.95, 1 minus 0.94, 1 minus 0.29, 1 minus 0.001. You can imagine this, but you will never find it. Why? Because when you're dealing with Boolean variables, it doesn't make any sense to write it down and create more confusion because you already have this value. So you know that you can just take this value and do 1 minus this value, and you will identify the probability for alarm to be false with these conditions. These are our conditional probability tables. In this case, these are priors. So this is the prior over burglary and the prior over a earthquake. So the parents that have no further parent will only have priors. So yeah, as mentioned in the previous slide, each row in a conditional probability table contains the conditional probability of each node for conditioning a certain case. These must sum to 1, as I have explained before. So this is the probability of true, and the probability of false will be 1 minus p. And so the second is usually omitted. Nodes with no parents, in this case, have only one row, and these are priors. And yeah, something relevant to look at is the fact that a node with k Boolean parents contains 2 elevated by k probabilities that can be specified. Okay. Oops, I moved too much. Okay, as I have mentioned already, the global semantics of a Bayesian network is the fact that the Bayesian network overall is representing a full joint distribution of the random variables that we are considering. And how this is done is really by applying several times the Bayes rule. So the product the joint distribution of n random variables will become only the product of the probabilities of these random variables given its parents. So now let's look again at this Bayes network, and we can try to compute what is the probability that the alarm has sounded, but neither a burglary nor an earthquake has occurred, and both John and Mary called. So this is what we're trying to compute: the probability of J, M, and A. So John called, Mary called, alarm has been ringing, but there was no burglary, no earthquake. So just as a reminder, this is the notation for not. Okay, So we're just going to look at this, and starting from j, we're going to say that this is equal to the probability of j given a, and we can forget about everything else, and the probability of m given a, and the probability of a given not b and not e, multiplied by the probability of not b and the probability of not e. So now let's try to put some numbers here. So the probability of j given a. So j given a. So a is true. So we're going to look at this. Let me use a different color. So we're going to look at this row here. This is the one that we are looking at. So we get 0.9 as a value. Also, probability of m given a. A is true. We're selecting this row. And we are using 0.7. Moving on, probability of a given not b and not e. So both b and e are false. So b is false, e is false. And we're looking for probability of a being true. So the value is 0.001. And finally, we're multiplying this by the probability of not b. So here we have the probability of b, but it is easy. We will do 1 minus 0.001, which is 0.999, multiplied again by probability of not e. Here we have the value for e being true. So again, we'll do 1 minus 0.002, which is 0.998. We'll do this product, and this is our final result. Okay, so note please that constructing a Bayesian network, a Bayesian network can be built in several different ways. So first of all, this representation of the domain is correct only if each node is conditionally independent of its predecessor, given its parents. And so in order to build a Bayesian network, you should first of all determine, as I've mentioned already, the variables that are required, and then you should order them following any order. So now, why did I say that you can have several ways for building a Bayesian network? Basically because the order that you use for your random variables, will change the structure of the network. So usually the suggestion is to move along this rule, which is ordering the random variables in such a way that causes come before the effects. So now that you created the nodes, then you can add the links. So basically you have to choose for all the random variables that came before the random variable that you are considering now, a minimal set of parents in such a way that this condition is satisfied. So the fact that the probability of the random variable given all the past variables is the same as the probability of the random variable given only its parents that you identified. Then for each parent you will just insert a link from the parent to the random variable, and then you will write down the conditional probability table. As a result of this information that we just got, we can also say that not only Bayesian networks represent full joint distributions, but also that locally they represent conditional independence. So the local semantics of Bayesian networks, in addition to their global semantics, is that each node is conditionally independent. Sorry, this came out very bad. Is conditionally independent of its non-descendants given its parents. So, looking at this is the random variable that we're looking at. Okay. Now, if we are given its parents, then this random variable is independent of its non-descendants. So the non-descendants will be this and this. So in this example here, for John Coles is independent of burglary, earthquake, and miracles given the value of alarm. Also, each node in a Bayesian network is conditionally independent of all the others given its Markov blanket. So the Markov blanket is composed by parents, children, and children's parents. So the parents again are, for this node X, the parents are these ones. The children are the following, and children's parents are finally these ones. Oops. So something people get confused a lot about is children's parents. So children parents means go to the children, and then you can have also other parents, not only this one. Okay, so for example, in burglary is independent of John Coles and Mary Coles given alarm and earthquake. So this part here belongs to the Markov blanket. Okay, so now let's try to answer some queries by using inference by enumeration in Bayesian networks. Okay, so what is the probability of burglary given the fact that John called and Mary called? So again, this is we can use the product rule, and this becomes a multiplication of alpha, so a normalization factor, by the probability, the joint probability of B, J, and M. Now here, if you're looking at this graph, we're talking about this term B, J, and M. In order to compute something, given that there is no direct relation between B, J, and M, we need to know something about alarm, and in order to know something about alarm, we need to know something also about earthquake. So we enumerate all the possible values that these random variables can assume, and use this for our inference. So that's why we do this summation here. Okay, so now let's focus on the case where B is true, and we can use the conditional probability table entries. So the probability of B being true given J and M will be alpha multiplied by the summation over E and A of this joint probability that allows us to use the Bayesian network itself and use the independence. So this will be the probability of B alone multiplied by the probability of V alone multiplied by the probability of A given B any times the probability of J given A and the probability of M given A. So basically, to compute this, we actually need to do a summation over 4 terms. So all the possible true and false values for E and A, so 2 times 2, and do 5 multiplications for each of these. So that's it. Basically, it's very simple. Okay, so this is showing you something how to proceed with the computation. Actually, you can move outside probability of B and probability of E from the all the 2 submissions in the case of PB and only from the last submission in the case of P of E. So actually computations can be made a bit efficient by looking at this graph. So we are going not to care a lot about efficiency though. So this is just for you to know. Now, we talked about this way of doing inference by enumeration, by looking at the conditional probability tables and so on and so forth. Doing this kind of computation in large networks, bias networks, is very hard, or is even intractable. So there are some randomized sampling algorithms that are called Monte Carlo algorithms. So Monte Carlo algorithms means that you're doing sampling. Basically, Monte Carlo algorithms are always doing sampling, and these provide some approximate answers, and their accuracy depends on the number of samples. So the goal again is to compute the posterior probabilities as we did before, but now we're sampling instead of using the full exact inference methods. So in order to do this, we can use direct prior sampling. So how do we sample values? So we sample from a known probability distribution, and we try to return the sample events. So the whole idea here is that we start with a variable, we sample the value for this variable, and then we move on to the next variable, and we do the same based on the prior ones, so based on the previous variable that we sampled. So basically you are conditioning your probability distribution on your parent assignments. So for example, we define a certain order, so we look at this Bayesian network here on the top right corner, and here we have 4 random variables, which are cloudy, sprinkler, wet grass, and rain, and we have these conditional probability tables. Of course, here we could do we have the conditional probability tables. The network is small, but this is just to give you an idea. So consider instead that you have a very, very large Bayesian network, and then you're trying to generate some samples, and then we'll see how we're going to use these samples. So we look at the random variables, we sort them, we create our own order, and actually, as mentioned, we start on the we consider the topological order. So we're going to start from cloudy, then we're going to sprinkler, rain, and finally wet grass. So we sample from the probability of cloudy, which is probability 0.5. So we toss a coin, we get true. So we color this in green, and then we assume this to be true, and we sample sprinkler considering this row because we decided that cloudy is true. So we look at the probability of this sprinkler to be true when it's cloudy. The probability of this it's very low and it's 0.1. The probability of this being false instead is 0.9. So we sample and we get false. So we mark this sprinkler variable as false in red. We go to our next random variable, which is rain. And again, we only look at this row because we set cloudy to true. So cloud is only our only condition. So the probability of rain given cloudy is 0.8. The probability of not rain given cloudy is 0.2. So we toss a coin. Actually, it's not a coin because it's not probability 0.5, but we sample from this distribution and we get true. Now we got sprinkler false and rain true. So sprinkler is false, rain is true. We look at this row here, and we know the probability that the wet grass is true is 0.9 under these conditions, and wet grass false it's 1 minus 0.9, which is 0.1. We sample from this distribution and we get true. So we return our samples as true, false, true, true. So now what do? We have computed these samples, and now we do this several times. So let's say we compute 100 of these samples, and then we count how often a specific event occurs in this set of samples. So we then use these counters in order to get an approximate estimate of the probability. So so basically, how do we do this? We divide the number, the counts for each specific event. This is divided by the total number of samples that we got. So in the limit, we should get that this corresponds to the actual probability. Now, your question might be, but if I have this thing here, why do I need to do this? So first of all, again, you might need to do this because you can't really compute your full your probabilities because you have complex computations to do. The other thing here could be that these samples are not actually coming from this prior sampling process, but they might come maybe from some actual observations. So this sampling could be in a different form. I go in the garden every day for 1000 days, and I look at the sky. I set it to true if it is cloudy. I check the sprinkler and I see whether that is on or off. I check whether it's raining, and I check whether the grass is wet, and I record this on my notebook for every day for all the 1000 days. So I do this, and then I can compute these probabilities by using these event counters divided by the total number of samples that I got. Something else that we can do is do a rejection sampling. So now we want to return an estimate of a conditional probability. So a probability of a random variable given some evidence. So the idea now is to generate samples from the prior distribution using prior sampling, reject all the samples that do not match the evidence, and then return an estimate of this conditional probability by counting how often the event occurred in the remaining samples. So it's basically the same thing, except that we remove all the ones where the condition is not respected. So here we have an example. So we're trying to compute the probability of rain given the fact that the sprinkler was on. So we have 100 samples, 73 of which have sprinkler at false. Only 27 have sprinkler at true, of which 8 had rain true and 19 not rain. So the probability of rain given sprinkler would be just the normalization over the number of times where rain was true and sprinkler was true, and 19 which is the number of times where rain was false and sprinkler was true. So then this becomes normalized, as I mentioned. So this will be 8 divided by 27 and 19 divided by 27. So let me write it down. Divided by 27. Now, there is a problem. If this evidence, if the probability of having this situation is small, that this evidence is something rare, then you are generating a lot of unnecessary samples and not getting what you would like to get. So the idea is now you can fix the evidence variables and sample only non-evidence, and then do some weighting. So this is called likelihood weighting, and let's look at this. So our query is probability of rain given cloudy and wet grass. So this is our evidence again. We have our usual order in cloudy, sprinkler, rain, wet grass, and we look at the execution of the algorithm. So we start by setting the weight to 1. We generate one event. So cloudy is the evidence with value true, and so we set this weight as the initial weight, which is 1, times the probability of cloudy, and this becomes 0.5. So sprinkler is not evidence, so we sample from this situation here. So sample from sprinkler given cloudy. So we look at this row here, and we get 0.1 for true and 0.9 for false. And let's say this returns false. So now we sample again rain from this row, because we know that cloudy is true, because this is our query, so we're fixing that evidence. And then we sample, we suppose that this returns true. Finally, wet grass is evidence with value true, and so we set our weight as the previous weight times the probability of wet grass given non-sprinkler, because sprinkler was false, and rain. So non-sprinkler and rain is the following: 0.9 multiplied by 0.5, it's 0.45. And then we return this event with a weight 0.45. Okay. Then basically what we do here is that the weight for each sample is just really the likelihood of the of that event. For every given sample is really giving us the product of the likelihoods for each evidence given the parents. So yeah, that's really the main point to take away here, is that you're going to use this weight here because this represents the likelihood of the sample under the conditions in the evidence. Okay, so there is another method that is very well known as MCMC, which is a short name for Markov chain Monte Carlo, that instead of generating every sample from scratch, it just makes new samples, creates new sample by making random changes to the previous samples. So for example, in the current state, we have a value for every variable, then in the next state, we do one mutation from the current state. And this is considered, this is done typically considering a specific form of Gibbs sampling. So the idea of Gibbs sampling, again, is that you start with an arbitrary state, you random sample a value for one of the variables that are non-evidence, so the ones that are not fixed, right? Because we cannot change the evidence. And of course, we sample condition on the current values of the evidence in the of the values of the variables in the Markov blanket, and in the evidence, of course, parents, children's, and children's parents. So yeah, and we keep the evidence variables fixed. So looking at one example, we do with our queries probability of rain given sprinkler and wet grass being true. So we keep sprinkler and wet grass fixed because these are evidence. So this is our evidence again. And we initialize randomly cloudy and rain. So let's say we get true and false. So our initial state is true, true, false, true. Cloudy is then sampled given its Markov blanket, which is sprinkler and not rain, right? So cloudy has its own Markov blanket in only its children here, because there are no children's parents and it doesn't have any parents. So conditioned on the values of these variables, we do a new sampling. And suppose that the result in this case is false, so the new state will be false, true, false, true. Then we look at rain again, and this is sampled from its Markov blanket, which is composed by its parent, its children, and its children parents. So wet grass, sprinkler, and cloud. So in this case, the values for these are non-cloud, sprinkler, and non-wet grass. And so we sample from this condition here, and we get true. So we get a new state, false, true, true, true. Then in the end, to answer to this question is that if the process to answer to this query, what we do is we continue doing this, and if this process visits 20 states where rain is true, and let's say visits 60 states where rain is false, then our result will be normalization over 20 and 60, So this will be normalized by dividing by 80, which is the sum of all the samples that we got, and this will be 0.25 probability for rain being true given sprinkler and wet grass, and 0.75 probability for that being false. So if you want to get a more detailed explanation on the Gibbs sampling, you can find this on the book, on the Russell and Norvig book. Let me write it down. Russell and Norvig book, page 537. Okay. This is everything for this part, so let me recap real quick what we have seen here until now. So we have seen, we started by looking at the Wumpus World, and we have seen that what you need to take home from this part of the lesson is that very simple problems can turn out to be very complex in terms of computations if you don't, if you're not smart. In the sense, if you do not exploit conditional independence. Sometimes exploiting this conditional independence can be very tricky, and you need to go through all this reasoning by yourself. So there are smart ways to keep track of conditional independence, especially when you're reasoning with Boolean variables. And one way of doing this kind of reasoning is using Bayesian networks. Bayesian networks offer a compact representation or full joint probabilities, and these full joint probabilities also allow us to identify very clearly conditional independence between variables. So performing inference over these Bayesian networks is much easier than not doing this, using them, just because the notation of conditional independence is very, very clear. Sometimes, however, it's not always possible to do an exact inference using Bayesian networks, and so for several reasons. And one way to deal with this and answer queries based on these networks is performing approximate inference. So this approximate inference can be done by exploiting sampling. And so based on Monte Carlo algorithms, we have seen a few different methods for sampling. We have seen direct prior sampling, where that allows us to basically compute joint probabilities, or in general probabilities of certain events. We have seen rejection sampling that allows us to compute some posterior probabilities based on some evidence and rejecting basically the samples that where this evidence is not respected. This has some problems, so we have seen the likelihood weighting, so where each sample is weighted by some weight that corresponds to the likelihood of that event. And finally, we have seen MCAMC, which is another method for sampling, where you are reusing the data that you already generated, so it's a bit also faster. You start from the sample that you currently have, and you mutate one of that based on the values of all the other variables, and you keep of course your evidence fixed because that cannot be fixed. So using all of this, you can compute your answer to your queries in a basically throughout sampling. So before closing, let me once again show you the Slido code. Please ask questions regarding this part of the class by using this code. Thanks for your time.